Okay, so next we have Milan Pes who will talk us about low mass contact binaries. So take it away.
Thank you. Hello, everyone. Sorry. I'm Milan Pes.
Right. It's the microphone.
Can you hear me? Is that okay? I'm Milan Pes. I'm a PhD student at Charles University in Prague. And before I start, I have a confession to make. Actually, I do not work on mass transfer. So I just have this. Just have this very neat result, which I think people that work on mass transfer might appreciate. So I'm going to talk about the method that we've developed to infer the minimum mass ratio of contact binaries. And to make my talk more attractive to people that work on mass transfer, I'm going to start with a brief overview of contact binaries, and then I will try to show how mass transfer affects the evolution of contact binaries. And then I will get to the description of our method, and I will give you our results. Okay, so I guess everybody or most of you have seen this author's rendition of what the contact binary looks like. The basic picture is that when two stars orbit too close to each other, they fill their envelopes and they form a single convective envelope, and a contact binary is born. Okay, so from observations, we know that regardless of the mass ratio, the effective temperature of the two components are nearly equal, which implies that efficient energy transfer must be happening between the two components. This is still not well understood till this day, but in the 60s and 70s, in an attempt to explain this, but also other characteristics of contact binaries, people like Lucy, Flannery, and some other people, they came up with this model in which the two components are not in thermal equilibrium, but actually they oscillate around the state of marginal contact. During these thermal relaxation oscillations, the two components bump mass between each other, and cyclic mass transfer on the thermal timescale occurs. On longer timescales, nuclear evolution and angular momentum laws drive. They drive the evolution towards small mass ratios, and I show this behavior here in this figure, which I adapted from Lee et al. 2004. You can see the evolution of the mass ratio of a contact binary over several thermal relaxation oscillations, and the simulation stops at about 0.5, the mass ratio, but actually the evolution generally goes to even smaller values, to extreme values, until the system becomes unstable to the Darwin instability. The Darwin instability is a tidal instability which occurs when the spin angular momentum of the more massive component exceeds 1/3 of the orbital angular momentum of the system. And because the parameters of contact binaries are highly correlated, this criterion, this condition on the angular momenta of the system translates to a condition on the minimum mass ratio of the system. And once the system crosses this threshold, the two components quickly merge. Okay, so we know that this thermal timescale mass transfer goes on until this minimum mass ratio, but how do we actually estimate the minimum mass ratio? So typical methods or standard methods would require a large sample, spectroscopy for a large sample of contact binaries, which is hard and expensive to obtain. Photometry is much cheaper and easier to get. And also in our solar neighborhood, contact binaries are very common. For every 500 main sequence stars, there is one contact binary. That means that we observe large numbers of contact binaries in photometric surveys. For example, in ZTF, catalog of variable stars, we observe 370,000 contact binaries, or in Assassin, 80,000 contact binaries. This allows the use of statistical methods and machine learning. So overall, we would be much better off if we could somehow infer the minimum mass ratio from photometry instead of spectroscopy. Lucky for us, in 2001, Ruchinsky published a paper in which he showed that the photometric amplitude distribution of contact binaries strongly depends on the mass ratio distribution of contact binaries. And you can see that here in this figure, where I show how the photometric distribution depends on the different values of the mass ratios. So now if you assume that the mass ratio distribution, and you assume some parametric prescription for that, for example, power law with a cutoff at the minimum mass ratio, when you combine it with the strong dependence on the prescription of the mass ratio distribution, you get a photometric amplitude distribution with local maximum whose position strongly depends on the cutoff that you choose. But to be able to use this to infer the minimum mass ratio, we require high precision photometry, which ground-based surveys just cannot provide. And for that reason, we had to construct our own sample, and we used the Kepler eclipsing binary catalog. I won't go into details about how we constructed the catalog, but the basic picture is we used Bayesian inference, and we modeled the Kepler eclipsing binary catalog as a mixture of contact binaries and Gaussian noise. And using this approach, we were able to assign to each object in the sample a probability of being a contact binary of either early type or late type. The difference being, in simplified terms, that late type contact binaries are have typically shorter periods and are colder, and early types are hotter and have longer periods. Okay, so this way, we obtain a sample of about 200 objects with probability of being a late type contact binary higher than 80%, with periods longer than 0.3 days. And here you can see the photometric amplitude distribution, the empirical one of this sample. And when we fit our prescription for the mass ratio distribution to this data, we obtain a minimum mass ratio of 0.087. We applied the same method also to contact binaries, to early types with periods below 1 day, and also to late types with periods below 0.3 days. And we obtained minimum mass ratios of 0.03 and 0.246. This points to apparent dependence of the minimum mass ratio on the period of the system, but most likely the dependence is actually on the composition and the mass of the system. This brings us to summary. So we developed a method for mass ratio distribution which doesn't require spectroscopy. We inferred the minimum mass ratios for three different populations of contact binaries, and we observed possible dependence of the minimum mass ratio on the structure and mass of the components. And importantly, this method is easily extendable to larger samples, which we expect from tests and other space-based surveys. That's all from me.
Questions?
So what is the physical interpretation of, you said a little bit about it, but this Q-min dependence on the period. So what do you think that results of?
Yeah, actually, my interpretation is that it has to do with the type of mass transfer. My interpretation is that it has to do with the type of the mass transfer which occurs before the formation of the contact binary. I think our results are roughly in line with the model of Stepien for the formation of contact binaries, which says that for these low mass contact binaries, depending on whether case A, B, or C happens, before the formation of the contact binary, the period, right, the extent of the system depends on the type of the mass transfer, and that affects the period and also the minimum mass ratio. It has to do with the ratio of the timescales of the nuclear evolution and the Anglo Maslow's timescale. We can talk about it later if you want. Yeah.
Thank you. Great talk. I was curious, can you say a bit more about this like Gaussian noise that you model? So is that also like includes binaries that are not contact binaries, or is that like any other data? I would love to hear a bit more.
Yeah, so here. Okay, so for these contact binaries, there is this period luminosity correlation, which I show here. And this results basically from the correlation of the parameters of contact binaries. So what I did is that I assumed that these contact binaries in the sample, they're generated from this probabilistic model, which is a line in this three-dimensional space. I gave it some finite spread, right, variation, but the orientation of the line and the spreads, there are three parameters. So I let the model decide, right, what's the best fit to the data. And I just modeled the rest, including all the other types of binaries, or they could be like some pulsating stars and so on. I just modeled it as Gaussian noise. And also, another free parameter of my model was the, so I modeled, right, the PLC relation as a broken line. And this was one of the, like the position of the break was one of the three parameters actually. And it coincides, so the craft break, I didn't mention this when I was talking about it, but the information about the craft break, that it did not enter the model at all. And we found out that the distinction between the two types coincides very well with the craft break. So yeah, it seems that the difference between the two types, it has to do with the position relative to the craft break.
Last question.
Thanks for a really interesting talk. I was just naive, or I kind of just missed, what is the difference between this early and late type, like the physical difference between them?
Yeah, so as I mentioned, most likely it has to do with this craft break, position relative to the craft break. And the difference is, that these early types, they have radiative envelopes, and late types have convective envelopes.
Okay, and then so you said the predictions match the observations.
Yeah.
Is that so? That's completely true for both sides. You're like all explained, or because there seems to just be so much scatter here that I don't know. Maybe I'm just a little confused.
I don't think I've said that.
Oh, I thought a few slides later you said the predictions match the observations.
No.
What did you mean there?
Not the observations, but the theoretical models of Stepien, right?
Sorry, what matches what? I just missed it, I think.
Yes, so my results for the minimum mass ratio, they are in line with what Stepien's model of contact binaries predict.
Okay, so it's not with this.
Yeah.
Okay, thank you.
Yes, because I mean, typically you get when you want to measure mass ratio of a contact binary star, you need spectroscopy, and for that, right, you cannot infer the minimum mass ratio of the full population because you can only do it individually for each. Right, you can just have like the smallest observed mass ratio, but you cannot say like this is the minimum mass ratio.
Thank you.
Okay, so let's thank the speaker again.